we're going to be doing enzyme regulation and inhibition. So first of all, aren't enzymes a good thing? Don't we want them to just make a whole bunch of stuff? And the answer is no, because sometimes you can have too much of stuff floating around. For instance, ATP, remember them? Well, if you have too much of them lying around, then you're going to have a lot of energy wasted because it's an unstable molecule after all. So like I was saying, ATP is unstable. So yeah, a lot of energy will be lost. So how exactly... So first off, what are inhibitors? Well, alright, so I guess it's best to draw this out for you. So I'm just gonna make this up. Here's a squiggly enzyme thing. Okay, this isn't squiggly at all, but the point still stands. Now it's going to bind to a substrate. Or, the thing it's transforming, catalyzing, whatever you want to call it. And let's say its active site is right around here. So, that's a normal reaction, and then, out pop two things. I mean, you can also just put two things in an enzyme and then get some, like, a thing out. It doesn't always have to be products coming out of just one single dot, but, and then these two come out. But that reaction might not need to happen. So what you do is simple. You block it. The first type of inhibition that we're going to be talking about is competitive inhibition. In other words, either the inhibitor gets there first or the substrate gets there first, and then the other one can't bind. So what it does is it mimics the substrate's shape. It's not going to look exactly like it, but it's going to bind right on in there. Of course, old Bluey over here can't exactly get in anymore. So it leaves. Simple. However, what if Blue got there first somehow? And now the yellow one can't stop the reaction from happening, so that's one type of inhibition. However, it can be overcome if you throw enough substrates at it. So it's imperfect in a way, but, So now yellow can get in. However, there is another way. It is called There's another type of competitive inhibition called allosteric inhibition. Allosteric competitive inhibition. And pretty much what happens here is also relatively simple. What allosteric inhibition does is, okay, fine, Blue can bind wherever the heck it wants on the active site. It can't, not bind on the active site. But I can prevent it from happening if I latch on somewhere else. But of course, as you can see, it's already here. Let me just put the yellow one. Oh, oops. Okay, there we go. Alright, so fine. The blue one can go wherever it likes, but it can just bind over here. It doesn't have to bind on the active site. And guess what? The blue one it can't bind to it anymore because it has been stopped by an allosteric competitive enzyme. So it can't get in. However, there is another type, non-competitive. And what happens here is the blue one can still bind to the active site. It doesn't matter if it gets there first or not. And even if the inhibitor locks on first, it still can bind on. But you know what? The reaction just won't happen, plain and simple. It just won't happen until the blue one leaves. And the yellow one decides to leave too. And it can do this by altering its shape. So, well, no, wait, that's different, okay. So yeah, inhibition, and that's how they regulate the enzymes. So let's answer these questions, and hopefully I did a good job explaining this to you. All right. First one. How do non-competitive inhibitors interact with enzymes? They bind to a location other than the active site, stopping the enzyme from functioning. That's A. B. They bind to the active site, preventing the substrate from binding. C. They bind to a location other than the active site, enhancing the enzyme's activity. And D. They bind to the active site, causing more substrate to bind. Now you're thinking, wait, aren't inhibitors supposed to stop the reaction from happening entirely? You're correct, because I forgot to mention one more thing. There's something called an activator. So an inhibitor might change an enzyme's shape to prevent a reaction from happening or an enzyme from getting in. However, an activator, so let's say the activator is this color, it can make the enzyme open up again or change back to its normal shape and encourage it to interact with other molecules. So then it might open up and look like this again. And now it can bind with the yellow. Of course, the activator can still be attached. It's helping out. So yeah, that's just the thing I forgot to mention. But anyway, the answer is A. They bind to a location other than the active site and just stop it from functioning. All right, number 2. What is the primary function of cofactors? All right, so this is another thing that I need to talk to you about. Now, enzymes are always portrayed as the stars of the show, but the truth is they can't do it alone. Sometimes they need a little bit of help. Now, they can either get help from just another molecule, not an organic one, not one that's alive or anything, but just maybe like a magnesium ion. Let me try it. Well, actually, no, I don't need to do that. Maybe it'll affect the way... Okay, maybe I do need to draw it because I don't think I'm going to be able to explain it to you. So let's say there's this enzyme here. I don't know, you can call it whatever you want. And this substrate here needs to bind to it. But there's a problem. The electrons just won't let it go. It won't let it go. So, magnesium ions to the rescue. I don't know where the gray is on this. Oh wait, now I remember. I can find gray wherever I want. So magnesium ions distract some of the electrons over here. I know this graph isn't exactly great because they're positive and stuff, so the electrons are occupied. Let me just draw some. Let's just say they're pink for now. Oh, didn't even change the color. Boop. All right, there you go. So now it's occupied. They're occupied, and the red one can go and join the enzyme. Now, cofactors can do things very similar to this, but they are organic molecules. They are like enzymes. They're alive. They're not just floating things. That was a bad way to describe it. I don't know. So let's draw another enzyme. I don't know. Let's make it yellow because, Now, the substrate might be here, but it still can't do the reaction without a cofactor to help it out. Maybe this one helps box off the blue one a little so that way it can go where it needs to go. I'm just making something up right now, but pretty much cofactors help enzymes. So that's the main point. What is the primary function of cofactors? To aid an enzyme function, to synthesize enzymes, to inhibit enzymes, or to break down old enzymes? And the answer is A. Disulfiram binds to the active site of the enzyme aldehyde oxidase, blocking the binding of a substrate. What kind of molecule is disulfiram? A. A competitive inhibitor. B. A non-competitive inhibitor. C. A cofactor. Or D. An allosteric activator. And it is A. A competitive inhibitor. And finally, pepstatin binds to the enzyme pepsin. The substrate is still able to bind to the active site, but the reaction is blocked. What is this an example of? Non-competitive inhibition, competitive inhibition, compartmentalization, and allosteric activation. Compartmentalization, by the way, is pretty much putting enzymes in places so that way they either don't cause trouble and endanger things, maybe keep it in a safe place since the environment isn't right for it, or maybe give it an environment to work in. So that's what that is. But the answer is A, non-competitive inhibition. And that's all. Thank you.